to welcome you today and thank you for joining us. Today our speaker is Joel Smith, who used to be the webinar coordinator for ASQ. He is a statistician and senior business development representative at Minitab Incorporated. He works with Six Sigma and quality improvement consultants and partners to develop new opportunities for the use of Minitab's software products. Joel has also worked with numerous companies on process improvement projects and initiative deployments. Smith joined Minitab in 2004 and has worked as a statistician and Six Sigma specialist since then. He earned a bachelor's degree in chemical engineering from Rose-Hulman Institute of Technology and a master's degree in statistics from Virginia Tech. Joel is a certified Lean Six Sigma Black Belt and past chair of the ASQ Statistics Division. And today, Joel will be presenting on the topic of non-standard measurement system analysis. Oftentimes, it is necessary to evaluate a measurement system where the standard 10-part, 3-operator, 2-replicate design does not work. In these situations, Gage R&Rs can still be performed and statistics can still be obtained. And using examples from the Olympics, Joel is going to demonstrate how. So during the presentation today, all phones and microphones other than mine and Joel's have been muted. So if you have any questions or comments during the webinar, please utilize the questions interface in the GoToMeeting control panel. And I'll pass these questions along to Joel and he can answer those for us. So without further ado, I'm going to hand things over to you, Joel, and thank you again for presenting with us today. Joel.
Okay, thank you, Amy.
Oh, okay.
So I'm going to start here. Can you hear me?
Yes.
I'll start today by going over what the standard measurement system analysis experiment is. It's probably something most attendees are familiar with. And then we're going to go into two very specific examples that don't really fit that mold. And I'll show how you can generalize a Gage R&R experiment to maybe answer specific questions or because you have other factors to take into account. So as probably virtually everyone on this knows, the standard measurement system analysis experiment that's taught uses 3 operators, randomly chosen, 10 parts, and replicates that 2 times. So it's very standard. It's published by AIAG, publishes that as the standard, and most Six Sigma programs have followed suit. So that's what most people would have learned in and the purpose of this experiment is to allow us to measure a few things. One is are the differences between operators. So do some operators maybe tend to measure a little higher than others, do some measure lower than others. An interaction between operator and part, so maybe there's something unique about a certain part that causes an operator to tend to measure that kind of part too large or too small. Repeatability, which is the ability for an operator to measure the same part multiple times with as little variation in their measurements as possible. And then reproducibility, which is really how much difference is there between 2 operators measuring operator differences and the operator-part interaction. Those are both the 2 components of what we call reproducibility. So those are all very useful things to know, and of course very important to do a measurement system analysis before you're going to use data for really anything, for capability, for control charts, for modeling. If you don't have high-quality data, that can either give you poor results or can make it very difficult to see important effects. So very important to do this, and by breaking things down into repeatability and reproducibility, and within that the operator and operator by part, we hope to be able to identify where most of our variation is coming from in a way that lets us go reduce that variations. In other words, it's very important if our measurement system is not performing well that we know whether that's a problem with multiple operators measuring differently. Maybe they need to be trained to do things consistently, or maybe you need a standard operating procedure. Or the other end of that would be even a single operator can't measure consistently the same part with the same measurement or very close to the same measurement, which would indicate any number of things, maybe a problem with the measurement device itself, poor training, things like that. So it's a very useful experiment for trying to separate those who don't, find out why and where we should go look for the problem. And the output, this may be a little less familiar to people. The output we get when we do a Gage R&R, shown here on the bottom box, shows things like the percent contribution. An equivalent is percent study variation. And it breaks things down by how much of that is from the total Gage R&R. Within that, what's repeatability, reproducibility, how much is part-to-part variation. All of that actually comes from numbers in that top table, which is a standard ANOVA table. May not be obvious looking at the top. So it's really just what we would call a general linear model converted to the standard Gage R&R statistics. And when we do this, there's a couple of things that are part of the standard, like the random effects. That means that that specific part of that specific operator aren't necessarily of interest so much as the variation between the parts or variation among operators in general. So it's assumed you're pulling each of those from a larger pool. In the case of parts, that's virtually always the case. You would never do a Gage R&R using every single part you've ever produced. In the case of operators, sometimes that's not a great assumption to make, but we do it anyway. And that's a topic for another discussion, but just want to point that out. And we want our part-to-part variation to be high and our Gage R&R variation to be low. Now those are relative to one another. Of course, you don't actually want the variation among your parts to be really high, but relative to the variation from your measurement system or your Gage R&R, you want most of that variation to be from parts and not from the Gage R&R. So you want it among the total variation of your data, part-to-part to be most of it, and Gage R&R to be as little of it as possible. So now we're going to look at an example here. This comes from the 2008 Olympics in Beijing. So we're going to look at 10-meter platform diving. That's the highest dive the athletes do. And in this case, the way this is set up is each diver in the competition gets to do 6 dives. Now, there's only a finite number of different dives that these athletes have come up with to do. So there's a whole listing of these dives, and each one has a degree of difficulty. So, of course, maybe just a big Swan Dive would probably be one of the lowest degrees of difficulty, and something you and I probably wouldn't know the name of would have one of the highest degrees of difficulty. Maybe 4 flips in the air and you twist, and there's various names for those. So they combine those into a single score. They multiply whatever your judging average is by the degree of difficulty, and that's your combined score. So that's how it works. Not very important to understand all of that, but I want to make sure everyone understands basically how this works. And of course, this is a judged event. So what we have is 7 judges. The judges can give each dive a score of up to 10, and they judge it in increments of 0.5. In other words, a dive can get a 7.5 or it can get an 8, but it can't get a 7.6. Going to be a 7, a 7.5, 8, 8.5, so on. So anywhere from 0 to 10, increments of 0.5. And they do this using 4 components of the dive. They can give you get off the board. You can get up to 3 points for flight. In other words, how well do you perform whatever flips, turns you're supposed to in the air. 3 points for the entry into the water. which, as most of us know, if you've ever watched even a little bit of Olympic diving, basically how little splash do you make going in. And then one is up to the judge's discrepancy. So how well just overall do they feel the dive did? Sometimes they may add those numbers up and say, you know what, those add up to a 7.5, but I really feel like that was a better dive than that. I'm surprised they add up that low. I'm going to give them the full point of discrepancy. Other times, maybe they add them up, they say, wow, those add up to 8. I don't know, there's something about that dive I was not very impressed with. I'm not going to give them any points for discrepancy. So that's how the scores come about. Now, to minimize the influence of maybe judges who didn't get a good look or have some other bias, the top and bottom two are discarded. For the purposes of today, though, we don't care about that because if there is some bias or some problem with a judge, we want to know. We don't care that their score keeps getting thrown out. We want to know there's a problem with that judge. We're going to use all scores. So here's an example of what our data looks like. You see the first diver here. This is just a tiny bit of the data set. There's a huge number of rows in this data set. So you see the first one, David Boudia. David's an American. That's him in the picture you saw in the beginning. And going on down through all the different divers, and I know the degree of difficulty, which score was given by which judge, and what dive number it was, 1 through 6. So we're going to make an assumption when we do this that there's no three-way interactions in the model. And we do this when we do regular Gage R&R. So I'm going to do everything just like a regular Gage R&R here. You have judges measuring something, right? They're taking measurements. We want to know how well will they do. How much of the variation is true variation between the performance of the divers, and how much of the variation is because the judges are inconsistent. These terms are fixed. Remember before I said usually we consider them randomly pulled from some broader pool. In this case, there's only 7 judges. There is no broader pool. We care specifically about those 7 judges, right? And likewise, our parts in this case are actually fixed, right? We don't care how divers perform generally. We care about the divers from the finals of the 2008 Olympics. And I'm going to analyze this. You can analyze this using general linear models. So some software would allow you to do what's called expanded Gage R&R, where it goes in and puts everything in. More generally, any statistical package would let you analyze using general linear model, and you just have to be able to convert things to those statistics that you would like. So our main effects in this model are the diver, right? Of course, we want to know which diver is better than others. The dive, so remember they do 6 dives. Well, you know, in the beginning, maybe divers are going to be a little more conservative, but you start getting near dive 6, you're in 5th place. You're going to go all out for the best dive you can do because that's your last chance to try to move into the medal. So as you move through those 6 dives, behavior may change. The dives may get better or worse as they go, or judged better or worse. We want to look at the judges, of course. We want to know if certain judges judge too high, certain judges judge too low. Just like in real life, you want to know if one of your operators tends to measure too high or measure too low. It's the exact same thing. Then we're going to look at 3 different interactions. There's a diver-dive interaction here. Now, the diver-dive interaction, a lot of times people struggle with interactions. This one's actually about as easy as it gets. The diver-dive interaction is actually what's being judged, right? When David Boudia dives and he gets a score of 7.5 from Judge 5, Judge 5 didn't judge David Boudia. He judged David Boudia's 3rd dive. That's the diver-dive interaction, the combination of the diver and which dive number it was. So that's actually what the scores represent, is the diver-dive interaction. Diver-judge is, of course, the one we always fear when we watched and judged event in the Olympics. A diver-judge interaction would indicate that certain judges are judging certain divers higher or lower than others. So maybe the American judge tends to judge David a little higher than the others. He knows he's American, he's seen him in other competitions, maybe he's given him a little bump. This is absolutely what we don't want to see among any judged event. This is what most people call a biased judge, right? That the judge is biased towards or against specific athletes. And then the third one could come up because maybe as we get later and later, a little harder in those later rounds. or maybe others start to judge a little easier. They kind of want to make things interesting, make it a little easier for certain divers to work their way in the medal round. Either way, it's conceivable that certain judges might change their behavior a little bit as you progress through those 6 dives. So if I analyze all of this data, I get an ANOVA table, and we'll just go piece by piece through this quickly. Oops. Of course, you have a p-value for all of these terms, and we're going to go through each one of these significant p-values to have a good look at, well, how much of the variation is coming from that term. You'll see we actually have a pretty good model. Our adjusted R-squared, it's 91.4%. That's a pretty good model using real data. Our residuals look good from the model. Nothing stands out too much. Maybe a few fairly low residuals, but nothing wild. So let's go through each piece of this. So diver, luckily, is a very significant factor. There is a difference between the scores different divers get. Some divers tend to get higher scores than others. Well, that's not particularly shocking, but good to see that the numbers back that up. And as we look, here's each diver and a plot of their mean score. So you can see, for example, the highest recorded diver here is Matthew Mitchum. You see another one on the end, Lucien Zhu. The third one, Gleb, I believe it's Galperin. And I've also drawn some dashed reference lines here. This is just, as you know, when you do any kind of ANOVA, you can do multiple comparisons and tell where you can tell differences. I put these just to see where you can tell differences between divers. In other words, you see 3 of these divers have scores above the first line. That means those 3 couldn't be differentiated using ANOVA. Then the next 2 couldn't be differentiated from one another. Then the next 3, then the next 1, then the bottom 3. Now you see poor David here has actually the worst of all the scores. It seems mean that I'm picking on the American diver from the competition. If it makes it acceptable in any way to pick on David so much, 4 years later David won the gold medal in the same event in the 2012 Olympics. So I feel like it's completely okay to pick on him here for 2008. So next we have a difference between the dives. So dive 1, 2, 3, 4, 5, 6, somewhere in there's a difference between the scores on those dives. And when I graph each of these, I'm going to keep them all in the exact same scales because that gives you a visual reference for how much variation is really coming from that. So you'll see here, that's a decent amount of variation here. Maybe not as much as among the divers, but it's a pretty significant amount of variation going on there. And again, I use those reference lines to tell where you can tell the difference. And as things progress, the mean score does go down. Now, that's not a completely shocking result. It doesn't indicate any judging problems necessarily. The judge-dive interaction would be a better indicator of that. What this probably actually means is divers are trying harder dives near the end and the scores are going down. That may be compensated by the degree of difficulty, but most likely what's happening is as you progress through the rounds, divers are getting more and more desperate to try to move up, and they're trying more and more difficult dives, which of course would result in lower and lower scores. Third one, judge. We won't look at a graph of this because it was not a significant p-value. We'll move on to the diver-dive interaction. Again, this one better have a significant result because this is what's actually being judged. And if we look at this, it's all over the place. That's fine. These actually would correspond to roughly the specific scores given to a dive. So you see your worst dive here. David Boudia actually didn't do terrible, but dive number 6. I'm not sure exactly what that dive looked like. I sort of picture him tripping off the end of the diving board and maybe doing a belly flop to get a score that low, below a 4. So under the individual scores of each dive, averaged, of course, across the 7 judges. Diver-judge interaction. So this has a very significant p-value, and this is the one that we fear, right? This is the judge bias that we always fear, that judges are going to favor certain divers more than others. And from a statistical perspective, it's a highly significant result, p-value 0.000. When we look at the graph, though, things don't appear, at least, as bad as they seem, right? This is looking across each diver on the x-axis, and you have the different judges' scores there. So although judges do differ diver to diver, you would expect these lines to be completely parallel if this interaction didn't exist, and of course they're not parallel. But they're also not all over the place either, so we'll get into some specific numbers around these in a minute. Then the last one is dive judge. This is a little surprising, but again, there's plausible explanations for this going in, so we keep it in the model, and sure enough, it turns out significant. And when we look again, although these clearly aren't parallel, they're also not all over the graph either. So what you mostly see is you have a couple of judges here. I would say across dive number 2, the judges were fairly inconsistent compared to the others, and dive 1 and maybe dive 6, which accidentally cut off in the legend there. But nothing wild. And again, we'll put firm numbers around these, so we're not just using our eyes to tell what's going on and to make up some story around them. So how would we break this up? So typically, we break up our variation when we do a gauge R&R into these things. We have our total variation. That's all the variation in the data, in the raw data. Then the first split we make is how much that total variation is actual differences between parts and how much is from the measurement system. That's the first breakdown right there. Then within the measurement system, we start to get more specific to figure out, well, if we have this error from the measurement system in these problems, well, what are they coming from? Is it repeatability or reproducibility? And if it's reproducibility, is it just operator differences, some measure high, some measure low, or is it other factors like that interaction? So we can do the same thing here. Even though we don't fit that exact mold and we have some different factors, we can use the exact same structure because we have the exact same goal to split these things the same way. So all we really need to do is figure out which term goes in which of these boxes. So I'm going to go ahead and place the terms here, and I'll just explain each one. And it's actually pretty easy to do this. It may seem like, boy, you have to go through every term and really think about this. So I'm going to start at the top, part to part. The easy thing to ask yourself to identify what goes in part to part is, if I could have absolutely perfect judges, a flawless measurement system, where would I still expect to see differences? Those are the items that are part-to-part variation. Okay? So that's all you ask yourself. If my measurement system was perfect, where would I still see differences? Well, you'd see them between the divers and the diver-dive interaction. And I should probably actually, to be honest, move dive up there as well, but it's a little hard to tell on that one specifically why there's a difference. So we'll leave it down below for now. Then repeatability is very easy. Repeatability is the residual error in the model. So the error term from that ANOVA table is your repeatability. Then reproducibility, differences between operators. In this case, is just judge. So who are your operators? Well, that goes in operator differences. And everything else that's measurement system error will go down here in other factors. The judge-diver interaction, the judge-dive interaction, those are all going to be other factors. And all of these things down here will add up to the measurement system variation. And here I'll actually do it. So when you do a general linear model on something like this, one of the statistics you can request are variance components from each term. So here I have the variance components from every term we want to look at. Some of these are adding up. So for example, judge, dive, diver judge, and dive judge, those 4 terms all add up to that reproducibility number. So it's pretty easy here to then just convert these into percentages. So we want the total gauge R&R, which I've highlighted with a red box here. That's what percent of the total variation in the data comes from the measurement system. And here it's 13%. Now, that would fail most people's qualifications for a measurement system. Typically, for percent contribution, people are going to look at a cutoff of 1% or less. It's going to be considered a good measurement system. Anywhere between 1 and 9% is going to be marginal, and above 9 is going to be considered an unacceptable measurement system. So next time you're watching Olympic diving and maybe you want to watch something else on TV and you want to annoy the person making you watch it, just casually say, you know, these guys can't even really tell the difference between divers very accurately, and I have the numbers to prove it. So it's actually not a great measurement system. We can break that down further. If we look through these numbers, we see that 8.3% is from repeatability. So that's the inability of a judge to consistently judge the same way over and over. And then 4.7 is reproducibility. When we look at that one we really fear, the diver-judge interaction, that only accounts for about 1.4% of the variation in the data. So that's actually, although emotionally that may be the one that we really fear, it's actually not a huge contributor here. And probably if you were to say we want diving judging to improve in the Olympics, that's certainly not the one you would attack first. In fact, that's one of the last things you would tackle. So again, how do we go through this? So we can sit, yes?
Do we have time
You
for
there?
a question here?
Sure.
Somebody is asking, where is the repeatability coming from since each judge only scores each dive one time?
That's a good question. So we actually do this. This is something you do in DOE or almost, well, I shouldn't say almost any kind of modeling. Most commonly in DOE, but does happen in other models. So think of doing a DOE, and you could put in, let's say it's not replicated, right? Just like this, no replication. You do a DOE, and you include every term in the model and every interaction possible. If you do that, you'll use up all your degrees of freedom and you have no error left over. Now, once you start taking out, say the biggest interaction is a five-way interaction, you start saying, it's incredibly unlikely that that exists in the real world, right? That's just not realistic. It shouldn't even be in my model. So you take those things out. You make an assumption that that kind of interaction doesn't happen in the real world. It's not realistic. You take it out. You now have some degrees of freedom left over, and those all go into an error term. And this is the same thing. You treat that error term the same way you treat the error from replicates. They end up the same way. Now, replicate's a shortcut to not have to make that assumption, but it's the exact same thing as doing that with DOE. You take the error term from your model. Let me go back here. So we have an error line just below this red box here with adjusted MS and everything else. That error line, we make the assumption that there's no three-way interaction going on here, and that any error left over is the same error, the same pure error that you would get by replicating and testing that. So it's actually a really good question, and it is an assumption. It's an assumption all of us make all the time, and most of us never think about making, because anybody who does DOE has done that exact same thing. And you're probably mostly all taught, don't even bother looking at three-way interactions and above. And that allows you to do much smaller experiments that way and make that assumption that any leftover error, which is really what those interactions would have been estimated as, is really like a pure error that would come up with replication. Any other questions right now?
There is one other question. Why are F statistics that aren't all that big so highly significant?
Well, okay, let's go back here for a minute. So when you look at these statistics, so you look at the F statistics, you see on the right side here, starting with the 163 and the 86. So those are only, so you can't really compare the different F statistics here to one another. For example, this 1.97, first off, these aren't calculated using the same degrees of freedom for what's the numerator of that statistic, so in this case 6, or even the denominator. Different terms are going to have a different, well, I don't want to get too much into general linear model, what's called expected mean squared that you're comparing it to. So that F statistic, the significance of that is compared to an F with certain numerator degrees of freedom and denominator, and each of these has a completely different number. So comparing it to each other is not possible. For example, you have for judge a 1.97, which resulted in a non-significant p-value. For diver judge, you had a 1.98, which was an incredibly significant p-value. But just considering the numerator degrees of freedom here, judge only has 6 degrees of freedom. Diver judge has 66. So it's an apples and oranges comparison. You can't directly compare those two. All right, any others before we move on?
That's all for now. Thank you.
Okay. Well, we'll move on and welcome any other questions. Okay. So just to summarize what we did here, so we had a clearly non-standard measurement system analysis to do. The interaction was really part of our part there. It's actually quite simple to convert that to what would be a standard gauge R&R. We're able to get the same statistics. We can compare them using the same cutoff points and identify whether a measurement system is acceptable or not. So the second example we want to do is going to be on pairs figure skating. And this example is going to be something some people may actually remember. I'm going to give the scenario here. So this was same year, I believe. And they used 20 pairs of skaters. Okay, so this is a team. You have a male and a female skater each time. There are 9 judges in this one. And the judges judge these skaters on 2 different categories. One is what they call artistic impression. The other is what they call technical merit. I'm not really a figure skating fan. I can't go in much detail. It has to do with the particular, what I would call tricks, right? The jumps and the spins, whereas artistic is more, I hate to use the word dancing, but more how fluid things are, things like that. So actually this is 2002. So 2002, they have what's called a short program and a long. And just after the short program, there's a Russian team in first and a Canadian team in second place. Okay? Now they go to do the long program, and actually remember when this happened, and others may as well. So after this long program, the crowd goes crazy. They think the Canadians have clearly won this. The commentators all think they've won. There's not even debate about it. And you could find video clips online of when this happened. You can hear that they think Canadians have clearly won this. But somehow the judges' scores come out, and the Canadians are in second place. They didn't win. They're still in second. Now, even stranger, after this happens, a French judge admits she was pressured to vote for the Russians over the Canadians. And then even stranger, later, she takes it back and says, no, I wasn't actually. I made it up. Now, this is pretty strange behavior, right? So why somebody would admit to doing something that would essentially be career-ending and then later say, never mind, I made that up, seems like very strange behavior. But rather than ask all those questions, because I don't think we can ever get a clear answer on that, I decided maybe if we analyze the data, we can tell whether that judge showed some bias towards the Russians over the Canadians or not. And let's suppose that judge was pressured. Maybe that means other judges were pressured too. So maybe we should look across the board. And this time, not only do we want to look specifically at any bias that might be going on, but we want to look at the Canadians and the Russians and see, does it appear that the Canadian team and the Russian team were treated consistently with how other teams were treated, or does it appear one or more judges may have been influenced? So here we have our data set again. Now this data set looks a little different, but you have a judge column. They're coded as J1, J2, J3. You have a rating column, so that's what the judges rated. And here you see they go down to the 10th of a point. So last time was down to half a point. These will go all the way to a 10th of a point. You have the name of the skaters. So and actually this includes both teams that we're interested in, the first 2 there. And then which category it was, artistic impression or technical merit. So our main effects here, of course, you have a judge effect, same thing, just like the operator-to-operator differences. You have the name of the skaters, so who are the skaters, of course, and the category, so which category are they being judged on. Then you have interactions. Judge name, again, is that bias. That's what, here we have a very specific question, and it'll be digging into the judge name bias, judge name interaction. You also have a judge category interaction. So maybe certain judges tend to give higher scores to artistic impression, while others tend to give higher scores to technical merit. So that would be a judge category interaction. How those do relative to one another depends on which judge it is. Then there's a name category interaction. So of course, certain skaters may be better at artistic impression than they are at technical merit. That makes perfect sense. So we have our same chart here. Just like the standard gauge, we can split all these terms up, and we're going to do it the exact same way. So we think about, if I had perfect judges, they were completely consistent, always consistent with themselves, always consistent with other judges, where would I expect to still see variation? Well, I expect differences between the skaters, that's the name, the category, right? I expect that artistic impression, technical merit, there's no reason those should come out with the exact same scores. Maybe skaters are generally better at one than the other. And the name, category, interaction, right? Certain skaters, of course, I expect to be better at one than the other. Again, repeatability is just the error term. Our operator term is just that judge column, so who are our operators? And everything else, we're putting in other factors. That's the judge name interaction, that bias, and the judge category interaction. We don't want judges to tend to do certain categories higher or lower than others. That's measurement system error. And again, we have an ANOVA table here. Now in this case, we have very significant p-values on every single term. Every term, 0.000, highly significant. Further, our R-squared adjusted is 99.03%. This is almost unbelievable data to have a real data set with people judging something and get that high of R-squared. Residuals, everything looks good in the model here. And now we're going to do the same thing. One by one, let's look at a few of these terms, and I'll keep them on the same scale once again. So here are each your skaters. Now I didn't do the multiple comparisons this time because we want to sort of work our way to that specific question of whether maybe there was bias towards Russians or Canadians. So as we look on here, we see how the different skaters do, and you'll see this first high point on the far left, that is the Russian team. I won't attempt to pronounce the name, so it's the one that starts B-E-R-E-Z. And then over here, the next highest point on the graph, that's the Canadians. And actually, believe it or not, that point is higher than the Russians. That's the Canadian team. Jamie Saleh is the first name listed there. Now for judging differences. This is why we put things on the same scale. Although the p-values may have both been tiny, it's very obvious looking at this graph that the variation coming between judges is much smaller than the variation between the skaters. There's very little variation here. You do have, you see Judge 2 here tends to judge a little higher than average. You come over here, Judge 6 tends to be a little lower than average, but these are pretty small differences. So 20 pairs of skaters, of course this graph is going to be busy. This is the bias term. This is the judge name interaction. This is where we want to see everything parallel. They don't have to be on the same level, but we want them to be parallel. And here you see there's certainly some differences going on, but this is a very busy graph to look at. Other than to say, yeah, I understand why it's significant, those aren't parallel. There's clearly some bouncing around going on in there. Now when we convert this, just like we did last time, to a table and we get our total gauge R&R, now our percent contribution is 2.7%. So that's quite an improvement. Last time we were above that 9% cutoff. We had about 13%, said this isn't even an acceptable measurement system. So here we're well within the marginal range, and even within the marginal range, we're getting down towards the good range. So we're not going to quite qualify this as a good measurement system, but we're certainly happier with the judging going on in the figure skating event relative to the diving event. And if you look within that and you want to see where different things come from, well, in this case, more of it comes from reproducibility than repeatability. And within reproducibility, interestingly, our biggest single source of variation is the bias, the judge-name interaction. So, although diving was worse, in this case, if we wanted to improve our measurement system, we would look at the judging bias first, as opposed to diving, where that would be one of the last things we would consider. But in our case, we have a very specific question. Good enough to know that that's the biggest source of measurement system variation. We want to know specifically, though, how about those Russians and Canadians? We're not that, we're not that worried if we mixed up the 18th and the 19th place teams. We're wondering, was there something going on that prevented somebody who deserved it from getting the gold? So what you're looking at here, I'll explain this for a minute, and then I'm going to highlight the skaters. So here we have the judges on the x-axis, so we can look at each judge. And what I've plotted is the coefficient for the interaction between that judge and each pair of skaters. So this is basically quantifying how much did each judge favor or disfavor each pair of skaters. For example, Judge 2, you have a point up here very high, highest point on the graph. Whichever pair of skaters that was means the biggest positive bias that any judge exhibited was Judge 2 towards that pair of skaters. No one else favored any pair of skaters more than Judge 2 and that pair of skaters. Likewise, on the bottom end, you see, well, there's a few down here. We'll take Judge 7, for example. So Judge 7 showed the biggest negative bias towards a pair of skaters. I haven't labeled which each pair of skaters is on this. They're all gray. We can't tell them apart. But this gives you some idea of what's going on. All right, so now I want to point out where are the Russians and where are the Canadians and where's that French judge. So we're going to look through here, and now I've highlighted and connected points here. The Russian skaters are highlighted in blue. So this is, the points in blue are the bias or negative bias for or against the Russian skaters by each judge. Similarly, the red line is the bias for or against the Canadian skaters for each judge. So before I point out which judge is which, a couple of comments to make here. There's actually very little bias for or against the Russian skaters. They were judged very consistently. Meanwhile, there's quite a bit of bouncing around for the Canadian skaters. Now, we can't tell everything from a graph like this and what's going on, and really, if we plotted every country on here, I don't know that the Canadians would bounce around any more than others. I just point this out so much to say it is clear that there's much more bias for and against the Canadian skaters than the Russian skaters. Now, it could be that the Canadian skaters were just difficult to judge. Right? The routine may have been very difficult. Maybe there was a slip-up, and different judges punish those kind of slip-ups more than others, right? Maybe there was something like that. Maybe they did a particular unusual trick, and some judges are more impressed by that trick than others. So we don't really know what causes this. We can't say there's anything malicious from this. So much to say there was definitely much more difference between the bias exhibited towards the Canadians relative to the Russians. So I want to point out here now which judge is the French judge. The French judge is Judge 4. So we look at Judge 4. Judge 4, there's no evidence of any bias whatsoever towards the Russian skaters. I should have put a reference line here at 0, which indicates no bias at all. The Russians are very close to there. The Canadians, she shows bias against the Canadians. Negative bias, hurt the Canadian score. However, when you look at this graph and you look at the magnitude of that bias, it's really not that unusual. I would guess in terms of negative bias, there are probably, I would say at least 20 points here that show more negative bias towards a pair of skaters than that French judge showed towards the Canadians. And likewise, if you look at the same magnitude, there's probably at least another 20 that showed a greater positive bias, including Judge 6, who showed a greater positive bias towards the Canadians than the French judge showed negative bias. So at least based on this, we would say, if she was pressured to try to hurt the Canadian scores or help the Russians, or whichever way the pressure went, it's unclear whether she actually followed through on that pressure. And if she did, she didn't appear to in a way that would affect the scores more than was already going on just in other judges, other biases, other things going on. So at least based on this, I would say it'd be very difficult to condemn that judge for bowing to pressure and having this bias or not. It is still a very strange story that she would admit being pressured and then take it back later. However, I think we can at least be comfortable that if judging bias caused the Russians to win this medal over the Canadians, it's pretty clear that that bias was not specifically because of Judge 4 favoring them. Maybe others, helped out, I'm not sure. But certainly it was not Judge 4 acting alone or anything like that would have caused this. The magnitude of this drop is far less than the overall score difference that ended up between them. So again, that's an example of answering maybe a very specific question we have. Now we still use the same method. We still found our equivalent standard gauge terms. We still assigned the variation to those, analyzed it with GLM, used those variance components to get our standard percent contribution statistics. But in this case, we also went in, we had a very specific question we wanted to answer. We were concerned about a very specific problem, and I think we were able to comfortably go in and answer that question. So that's what I have for now. If we have questions, I'm more than happy to answer.
Thank you, Joel. That was very informative. There aren't any more questions that have rolled in. Somebody was having an issue with the audio, but I'm going to recommend watching the presentation once it's posted to our YouTube channel.
Okay, perfect. My email's up as well, so if anyone has questions and wants to contact me, I'm open to that. Please feel free to send me an email.
Actually, we did just get one in. Somebody is asking, how did you decide on your metrics for what a good measurement system is?
Well, so those are sort of standards that are taught places. When I say that, if I go back to this table and we talk about that percent contribution number, the 1%, 9% cutoffs are numbers that are commonly used. I wouldn't take me presenting those as being an endorsement that those are the perfect numbers. I actually don't like that there's formal cutoffs because I don't like somebody treating a measurement system with 8.9% contribution differently than 9.1 when those are really about the same. So I present those as the standards most people are familiar with, but I don't know that I necessarily endorse them. I do like to use percent contribution for a couple of reasons. One is those are additive, right? So if you use percent study variation, they don't add up to 100 and it gets weird. Also, it's an easy interpretation for me. I can look at this and I can say 2.7% of the variation in figure stating scores are due to the measurement system, are due to judging errors, judging bias, those things. That to me is a pretty simple thing that I can explain to someone. 2.7% of the variation in the data is because I can't measure perfectly.
Okay, that's a pretty comprehensive answer. Thanks. Okay, so I'm going to recommend that if since there are no more questions, that if anyone does have a question after the presentation, that you just send Joel an email, jsmith@minitab.com. But that was an excellent presentation, and a recording of this webinar should be available within a few days on the Statistics Division's YouTube channel, and you can find that at youtube.com/ASQStatsDivision. So be sure to share this webinar and our other archived webinars with your coworkers or whoever you think might be interested. Also, we encourage you to check out the division's LinkedIn page. It's a good way to stay connected with other quality professionals, as well as see announcements on webinars, conferences, and other technical discussions also. And check out our events calendar at asq.org/statistics. And Joel, are you going to make a PDF version of your slides available? People are asking.
Sure. If somebody wants to email me, I can respond and send that.
Okay. All right. Well, I think if there are no more questions, then I think that's all the time for today. So Thank you, Joel, and thank you all of our attendees.
All right,
And I hope
yes.
everyone has a good weekend.
Yep, thanks to everyone for attending.
Thank you.